of the bus bars. Now we're going to study the magnetic field due to current flowing in this copper rod. We're going to explore it with the help of all these compass needles here. Now right now they're all pointing approximately north and south due to the Earth's magnetic field. I say approximately because this is, after all, a magnet laboratory, and there are plenty of stray magnetic fields around here that are as big as, if not bigger than, the Earth's field. Okay, Beans, let's have about 1,500 amperes through the wire. And now you can begin to see some activity. They wiggle around and start to line up in the form of circles going right around the rod through which the current is flowing. All right, Beans, let's reverse the current now. We have to turn it off first and then reverse it. Now, you think you can see what's going to happen? We're going to turn around and point the other way. Now you can see they all point in circles around this way. Okay, Beams, that does it on the current. Cut it off. The lines of magnetic field are circles around the current, and they reverse direction when the current reverses.
Now we want to show you an experiment involving this good old lecture demonstration magnet, which isn't part of the magnet laboratory at all, really. We need to have a magnetic field, and we can get it here between the poles of this magnet very conveniently. I'll just turn it on. Oh, I better watch my watch. I get it magnetized so much I get sick of having it demagnetized. I have to get along with just setting it every time I see an electric clock. Well, now we have a magnetic field here, and there's a very simple little way of showing this with a few little nails. I think you can see that we have here a magnetic field going from this pole to this one. Now we want to talk about the forces on a current-carrying conductor in a magnetic field. In an earlier experiment, we showed you about the forces between currents. Now we want to leave out the notion of the other currents and really discuss just the force on the conductor in terms of the magnetic field which is present where the conductor is located. I'll put this in here, and we can pass a current through it, through the little mercury cup into which it's dipping by means of these wires, so that we'll have a current at right angles to this magnetic field. All right, let's turn this on. I think you saw that we had here a vertical force upward on this current-carrying conductor when it was at right angles to the field. And whenever you have a field like this, horizontal, with a conductor carrying current at right angles, we'll have a force at right angles to both, an upward force in this case. Magnetic fields are produced by electric currents. In a circular loop of wire of this kind, a circulating current will produce a magnetic field that goes through the wire. If we have a whole series of turns of this kind to form a cylindrical coil, the magnetic field will be driven in at one end and out of the other. This is, in effect, a cylindrical magnet, and we want to discuss whether we can describe the magnetic field produced by a magnetized iron bar of this kind in terms of currents. Clearly, we have strong magnetic effects of some kind, and the question is whether this must be described in terms of a new concept of poles in a piece of magnetized iron, or whether currents will do. If currents can be considered in this connection, they must, of course, be atomic currents, not macroscopic currents. There are no wires connected to this, and this is a problem for atomic theory. An atom may be thought of as having a positive nucleus and a cloud of negatively charged electrons around it. And if this cloud of electrons is rotating, it will produce a circulating current of this kind, and the field due to this current may be thought of very much like the field due to a circulating current through the wire. It will drive flux or magnetic field through the atom. And if we have a lot of these side by side, they will all drive field through the individual atoms. And in a magnetized piece of iron slab of this kind, we may think of magnetized atoms as being lined up so that the currents are circulating in the same direction, and these circulating currents drive flux through the whole business and produce a field very much like that which is produced by the single circulating current in this wire. Now, if we take a lot of slabs of iron of this kind that are magnetized and put them together to form a cylindrical rod, we see that all the circulating currents of the individual atoms may be thought of as driving magnetic field through the whole magnetized bar and out of the other end, and producing an effect very much like that of a solenoid of this kind. Now, John has been setting up our last experiment, and we want to examine a little further the nature of this comparison. Now we want to show you in this last experiment a little bit more about the nature of this interaction of a current in a conductor with a magnetized magnet. That's what John's been setting up here.
Well, here we have a pair of electromagnets. They're coils of wire through which we can pass a current. Now, we've arranged these in such a way that the magnetic field due to this one is in the opposite direction as the magnetic field due to this one. And we shall detect the magnetic field at this point in the center by means of a compass needle.
So this turns out to be kind of a magnetic balance,
That's the idea. When we get them exactly balanced, there won't be any magnetic field right in the middle, so that the compass needle will show.
Well,
why don't you put on a little current through yours? We'll see what happens. So there we have current flowing through this one, a magnetic field attracting the compass needle. All right, now I'll turn mine on and see what we get. So far, just exactly nothing. So let's raise the current a little bit and give her a spin to get it off dead center.
Well, that looks as if yours, well,
now
just about
balanced. Mine's going to be stronger than yours now.
A little bit stronger.
Yeah, okay, so I'll back mine off a little bit and make it a fair game.
Now it's weaker.
Now, here we have a bar of iron. I'm going to put the bar of iron inside this magnet so that the iron will, as you know, become magnetized, and its magnetic field will add to that of the current. Well, it looks like I'm winning this time. See what you can do.
I don't know.
Here.
Haven't got very much poop here, but I have an idea. What do you say if we try to connect up the old iron sides out here and see if we can put enough current through that copper winding to counterbalance what looks like currents flowing around that iron rod?
Okay.
There's one bus bar connected onto here through a couple of good straps. And there we are. Now, are we all clear?
Fire away.
Okay, Beans. I guess we're ready for a little juice.
Okay, here it comes. 1,000.
Keep going, yeah. Oh. I guess we haven't made it yet. Oh, it's beginning to melt. Oh, we haven't made it yet. Okay, Beans, I think that's enough. Well, I guess we didn't have quite enough current there to really equal the magnetization of the iron. I suppose it's clear now that the magnetic effects of magnetized iron are stronger than anything we could produce by driving currents through those coils. How is this possible? It's because within each iron atom there are such strong circulating currents. Because in the iron rod we were able to line up these currents, and finally, because in the rod there are so very many atoms.